My name is David Hicks, and today in this session 2, we're going to be discussing AFLOW-SYM, and this is the AFLOW built-in symmetry software to calculate the crystallographic symmetries of, for example, these postcard files or these geometry files that we've been creating. And so I wanted to motivate this section by basically highlighting why symmetry is important. And the overall goal here is we want to better understand the structure, so that way we can help better guide materials design. So for example, for symmetry, for instance, it's important, or you can use symmetry to determine whether or not a particular material exhibits certain properties. And one of the prototypical examples is piezoelectricity. So for example, let's say that you have a crystal structure, let's say the half-Heusler structure, that doesn't have inversion symmetry. If you were to apply a force on either side of the material in this kind of uniform direction, you would basically observe an accumulation of charge as you apply this force, and you would see a voltage across the material. And so this is basically the phenomena of piezoelectricity. So apply a force and you observe a voltage. And so this occurs for systems that don't have inversion symmetry. But if you have a particular system, let's say diamond, that does have inversion symmetry, if you were to apply the same force, you wouldn't observe this voltage across the material. And so you can use symmetry as a way to screen or filter out properties, or excuse me, materials that would be good for piezoelectric applications. And so this is just one example of how symmetry can be important for materials design. The other component that I wanted to highlight, or another example, is we can, again, use symmetry and structure to basically automatically generate new materials and guide materials discovery. So we saw a little bit of this yesterday, and I'm going to discuss it actually more in session 3. But essentially, we can take a backbone structure, so crystal structure, and it doesn't have any atoms decorated onto it yet. These are just sites with no elements on them. But we can go to the periodic table, and then we can decorate different elements onto these sites, and these sites have certain symmetries. And basically, these positions are fixed, but we're changing the elements. And so we can see here we have the band structures, and we can see that all of the band structures look the same for the same structure material, but they look slightly different because of the elements that we've placed on them. And so, for example, you can see the band gap is tuned slightly depending on what elements are decorated onto this structure. And so again, this is another aspect of where we can, by better understanding the structure, we can tune or guide materials design for certain applications. And that's really the motivation behind this. So it looks like there's a question in the chat about the VPN. So it looks like, I don't know if somebody can maybe redirect, oh, just the virtual machine. We may need to have you go into the breakout room with Marco, because it seems like if there's too many tries, then your account may need to be reset so that way you can add in your password correctly. I don't know if one of the other co-hosts can add Megan.
Yeah, I will move over to another room.
Okay, we'll do. Oh, okay, and it looks like Dr. Esters is here too. Okay, thanks guys. Okay, so yeah, this is the overall motivation: better understand structure to control the properties. And that's really where this where we hope this section will be useful. Okay, so as I said, we're going to be discussing this AFLOW-SYM software that we've developed in the AFLOW consortium. And so AFLOW-SYM determines the invariance of a crystal under transformations. So for example, we have an arrangement of atoms and we're trying to find the mirror planes, the rotation axes, so 3-fold, 4-fold rotations that basically map the crystal back onto itself when the rotation is applied, or the transformation is applied. And from this information, we get common symmetry descriptors, if you're familiar. So we get the space group, the Pearson symbol, the Bravais lattice, the Wyckoff positions. And then we can also, based on the symmetry, convert the cell into a particular representation that kind of highlights the symmetry. So for example, the conventional or primitive cell. And as we'll see today, and also I think throughout the rest of the week, we'll see that symmetry is a very important aspect of the AFLOW software, and it's used in many different modules. As we saw yesterday, it's used in the Brillouin zones determination. So if you recall, when we were determining the band structure for the silicon in the diamond structure, we needed to know that it was an FCC structure or lattice. And so again, that requires a symmetry analysis. So if you're doing anything related to band structures, you need to know what the symmetry is so you can project along the high symmetry K-paths. So symmetry is used there. We'll also see that it's used in phonon calculations. I believe we'll see this on the last day. And we can use symmetry again to basically plot the phonon band structure along these high symmetry K-paths. But it can also be used as a method for reducing the cost of simulations. So for example, for phonon calculations, we're basically representing, or we're modeling these phonons via distortions of the atomic positions. And so you can use symmetry to basically determine which distortions are symmetrically equivalent or inequivalent. And so we can use symmetry as a speed up here. Additionally, as we'll see in the next session, we can use symmetry to classify crystallographic structures or prototype structures. And then finally, we saw a little bit of this when Professor Toer was showing the AFLOW database, but we also use symmetry to characterize all of the materials in the AFLOW database. And so since symmetry is used throughout all of these different modules, it needs to be very robust. And so one thing that I want to highlight about the software is that there are 3.5 million entries in the AFLOW database, and AFLOW-SYM is able to accurately characterize all of them. So there's no human intervention needed. You don't need to play with any parameters. It's all done automatically without human intervention. And so again, as a user, that's very nice for you because you don't need to constantly play with parameters to get consistent symmetry results. And so what I want to highlight here are some of the subtleties on how we actually calculate these symmetries in AFLOW-SYM to kind of highlight the problem a little bit better. So so it looks like there's a question. May I ask, what is the platform of the database? I guess, can you clarify your question a little bit? I guess maybe one thing that I'll say is that Dr. Esters is going to be talking about the structure of the database and basically the API, so the REST API and search API. So maybe that'll answer your question. And he's going to show you how you can access the data. So if you have if you wanted to clarify on the question, or perhaps maybe waiting until day 3, I believe day 3 or day 4, we discuss the database. Okay, it looks like we have another. All right, so it looks like for the database, which software was used to create the database? I mean, so the AFLOW software basically does all the calculations, and it's stored basically kind of in a file system structure, and then we use these APIs to query the data. If you're talking about a particular, yeah, I guess and I don't know if any of the other AFLOW instructors understand the question better, but I think.
Yeah, there's no software. We create the software for it. The database is the entries that we create are stored in a file system format.
Right.
So it's, I mean, we're going to be talking about our APIs in some of the later sessions. Now those leverage we have some SQLite software that we use for storing some of the properties, but fundamentally the database is a file-based system database.
Right. Awesome. Thank you, Dr. Osis, for clarifying. So yes, yep. And yeah, Dr. Esters will be discussing a little more in detail, I think tomorrow or Thursday. So but good question. So it looks like there was another question. Does AFLOW estimate how much a symmetry is broken? I guess there kind of is a degree that we can kind of measure that, and that might come into play with actually the tolerance values. And we'll see that actually in the next few slides. And basically, depending on, if you change the tolerance, the symmetry tolerance a lot, you may be able to kind of quantify whether or not, this particular system is prone to exhibit symmetry breaking. So I'll actually discuss the tolerance in a little bit, and hopefully that'll answer that question. But great question so far. So I guess coming back essentially to this tolerance value is described on this slide here. So the idea that I want to highlight here is how we actually identify symmetry elements computationally. So let's say that we have an arrangement of atoms. So we have this diamond arrangement, and we want to know whether or not it exhibits a particular symmetry. So for example, this fourfold rotation. And so to do this, or to model this or determine this computationally, we basically need to take the atoms, apply the transformation, and see whether or not the transformed atoms map back onto the original atom positions. And so when we do this transformation, there's essentially 3 possible outcomes exhibited on the right here. So in the ideal scenario, when we perform the transformation, the atom positions line up exactly. And so this is an easy way to say, okay, this particular transformation applies to our crystal. And so we would say that this particular example of atoms exhibits fourfold symmetry. However, on the other end of the spectrum, we might get this scenario here at the bottom. So when we apply the rotation, we actually don't map back onto atom positions. And so we would say that this particular arrangement doesn't have fourfold symmetry. And in this case, it actually only has twofold symmetry. But actually, the most realistic or the most common scenario we encounter is in the middle here. So when we apply the rotation, the atom positions don't line up exactly back onto the original atom positions. And so the question is, should this be a mapping? And so this is where this idea of a tolerance threshold or a threshold for mapping comes into play. And since we're working with real positions, the atom coordinates may not be ideal with respect to the symmetry. Again, these are real crystals, so they're not necessarily going to sit on the mathematically pristine positions for the symmetry. And so we essentially apply a tolerance threshold. And so, if the atom positions are within this threshold, then we would say that the atom positions map, and this is an isometry of the crystal. And so in general, the idea here is that we take the original atom positions and we compare them to the transformed atom positions. And if all of the distances between these mapped atoms are less than this threshold, then we would say that this is a consistent mapping and this is a symmetry of the crystal. But there are kind of 2 subtleties or difficulties that I wanted to highlight. One is periodic boundary conditions. So as Dr. Osis showed, basically how we model a macroscopic crystal is basically with this finite unit cell. But we need to keep in mind that basically in this unit cell, it's repeated everywhere. And so basically when we're comparing distances, we need to consider the distances in neighboring cells. And so we need to consider periodic boundary conditions. The other difficulty is we need to be careful when we're performing these distance mappings in non-uniform metric spaces. And I'm going to highlight that in the next slide. So what do I mean by this? So typically, when we're modeling crystallographic structures, we can kind of represent them in 2 different coordinate systems. One is a Cartesian coordinate system, which is a Euclidean metric, so it's a uniform metric. However, as we saw yesterday, we also represent the crystal in a fractional basis. And so this is not necessarily a uniform metric, because as we saw, essentially all of the atom positions are between 0 and 1. And so essentially we're converting any lattice into a unit box, regardless of what the lattice actually looks like. Everything in fractional space looks like a unit box. So what is the consequence of this when we do mappings? So to highlight this, let's say, for instance, we have a cubic lattice in Cartesian coordinates. When we represent it in fractional coordinates or do this transformation, we see that we just get a uniform compression of the space. And so and if we consider this sphere here, this is just a pictorial representation of that epsilon sphere, so that tolerance. And so we see we just get a uniform compression of the space when we convert a cubic lattice into its fractional counterpart. But if we have an orthorhombic lattice, so it's a little bit longer, again, we're converting to fractional coordinates. We're basically converting it into a unit box, so we get this compression of the space. And so we're seeing how the metric or the metric tensor changes within this space. And in the worst case, the triclinic lattice, when we do this transformation, we get the shearing of the space. And so what this highlights is that when you perform the transformation between Cartesian and fractional coordinates, your uniform or your metric tensor is not necessarily uniform anymore. So you need to be careful when you're doing mappings. So how does this come into play actually? So let's say that we have this 2D crystal here. And let's say we have these blue atom positions. And then we want to know whether or not there's a mirror plane essentially along this axis here. So again, the procedure is we take the atom positions, transform them based on the symmetry element. And now we have these new atom positions represented by these hollow spheres or hollow circles. And so we need to do a minimum distance calculation between the original atom set and the transformed atom set. And so in Cartesian coordinates, it's straightforward, but a little expensive to find the minimum mapping distance. But if you do the same in fractional coordinates, again, you're converting your system into a unit cube, or in this case, a unit square in 2D. And if you were to do the same minimum distance calculation here, you would actually find that this is the minimum distance. So this, you'll notice that we map to two different positions. And so what I want to highlight here is that minimum distances in fractional space don't necessarily correspond to a minimum in Cartesian space. And again, that's highlighted here. We see this difference in mappings. And so I know that I kind of went into the weeds with these technical details, but the take-home message here is that AFLOW-SYM takes into account the skewness of the lattice when it does the mapping procedure, and it finds consistent mappings regardless of what space we're working in. So essentially, it can handle non-uniform metric space mappings. So that's one way that we're able to get highly or consistent results. The other two things that I want to mention is that AFLOW has an adaptive or self-consistent tolerance scan. So what do I mean by this? So let's say that we have a particular crystal system and we determine what the symmetry is at different tolerance thresholds. So for example, this is a tolerance number line and we calculated the space group symmetry. And so on the left-hand side, we have tighter tolerances and we would observe lower symmetry, as you might expect. But as you loosen the tolerance criteria, you might be able to find more mappings. And you can see that on the higher end of the tolerance spectrum, you get higher symmetry. And this is actually a real system that we encountered in the inorganic crystal structure database. So this is not a fictitious system, this is real. And you can see that we get essentially different space groups depending on the tolerance value. But one thing I want to highlight here is that there's this void region. And this is what we call a confusion region in the tolerance spectrum. So essentially at this particular tolerance value, the algorithm, the AFLOW-SYM algorithm, found inconsistent symmetry. So for example, maybe it found 49 point groups, which is impossible. And so instead of throwing an error, basically AFLOW-SYM will do a radial tolerance scan from that position and calculate the symmetry at a new tolerance value until it finds consistent symmetry at a new tolerance value. And again, this is done automatically for you in the AFLOW-SYM software. So you're guaranteed to get a consistent symmetry regardless of what your input tolerance value is. And then one of the last things that I wanted to mention about the technical details is that AFLOW-SYM employs a system-specific tolerance value. So if you're familiar with some of the other symmetry packages in the community, a lot of times they specify one tolerance value that applies to all of their systems. Maybe it's 1/100th of an angstrom, for instance. But on the other hand, AFLOW-SYM employs a system-specific tolerance value. So it takes into account the resolution of the crystal, essentially. So it takes the minimum interatomic distance in the crystal, and scales the tolerance threshold accordingly. And so there's two default thresholds that we have. So epsilon tight, which is our default, is the minimum distance divided by 100, and epsilon loose, which is the minimum interatomic distance divided by 10. And the last thing that I want to mention about this is that AFLOW-SYM employs one single global tolerance value. So again, if you work with other packages in the community, sometimes they have angle tolerances or distance tolerances, or even tolerances for particular rotations. And so as a user, that can be a little bit cumbersome. And so AFLOW-SYM uses this one global tolerance for everything, and it converts it accordingly to angle tolerances, distance tolerances. And so as a user, you don't need to worry about all of these technical details. All right, so I went through all of these details, and so maybe your question next would be, okay, so how does AFLOW-SYM perform against some of the standards in the community or some of the other packages in the community? And so we did this benchmark. We took systems in the inorganic crystal structure database, and from this data set, they report the experimentally determined space group. So from the experiment, they maybe did XRD or something, and they found the space group experimentally. And then we went to the software packages and based on the coordinate information, had them calculate what the symmetry was. So basically we're comparing experiment to computational calculation. And here we plot the mismatch. So basically the higher this number is, or the taller these bar lines, the worse the package performed. And so basically we're plotting when experiment and the calculated package do not agree on the space group. And here we've kind of outlined it based on lattice type. And so blue is AFLOW, green is FineSym, red is Platin, and yellow is SPGlib. And so you can see in general, AFLOW has the fewest number of mismatches, so it's the most consistent with experiment. And you'll notice that these other packages essentially have solid bars and also slashed bars. And what this shows is that in general, we use the default tolerance values for the respective packages, but we also changed the tolerance value for these other packages. So essentially we tried to change the tolerance, tune the tolerance to see if we can maybe get better symmetry results, because maybe it's just an impact of tolerance value. And you can see that, you know, if you change the tolerances for these other symmetry packages, you can lower, or maybe sometimes it increases the mismatch. But what this highlights is that as a user of these other packages, you'll need to play this tolerance number game where you're kind of playing with the tolerances for each system. But the advantage of AFLOW is that automatically, if you use the default settings, default tolerances, you'll get consistent symmetries. And as a user, you don't need to play with any of the inputs. All right, so again, if there's any questions about what I've discussed so far, feel free to post in the chat and I'd be happy to answer any questions. So those are kind of the technical computational details. And so now I'm going to highlight what you can actually calculate with the software, and then we'll start getting into some demonstrations. So the idea here is, again, the AFLOW-SYM software is determining these isometries of a crystal. So we're determining things like the rotations, so twofold, threefold, fourfold, and sixfold. And if you're familiar with the crystallographic restriction theorem, basically these are the only possible rotations in a periodic system. So we're trying to find these rotations. We're also looking for inversions. So basically you have an inversion point and basically the element transforms or inverts through that point. We're also identifying roto-inversions. So this is a rotation followed by an inversion. So for example, if you're looking at this symbol here, this threefold roto-inversion, so you would rotate 120 degrees and then invert about this inversion point here. And so basically that's a roto-inversion. And it creates this constellation of points. So basically by applying this rotation or roto-inversion, you're basically forming, there's points at all of these positions. So we're finding roto-inversions, we're finding glide planes. So this is a mirror followed by a translation. And then we're also finding screw axes. So basically it's a rotation followed by a translation or a compound operation of rotation and translation. So basically this point here is rotating and translating up to here. And here's a few variants here. And so from these different symmetry operations, we can collect them and put them into groups. So if you're familiar with group theory, basically these are elements of our group. These rotations or these operations are elements of our group. And so a lot of times we'll refer to things like the point group. So these are a group of rotations, inversions, roto-inversions. Then if we add in translational invariants, again, since we have a periodic system, then we basically are introducing more elements into our group. So we're adding in the screw axes and the glide planes and also lattice translations. And this gives us the space group. And then one kind of maybe group that people may not be familiar with, I believe Professor Cordarolo mentioned this in his keynote talk, but there's also what we refer to as the factor group. And basically this is the coset decomposition of the space group. And what this means is basically we're separating the lattice translations with respect to all of the other operations. And so without getting into kind of the mathematical details here, essentially all this means is that we're determining the symmetry confined to a unit cell, because the space group is with respect to infinite space, but the factor group is the symmetries confined to a particular unit cell. And so this is really going to be important for modeling. Again, we refer to everything in the unit cell. And so this gives us the symmetry of the objects within a particular unit cell. It could be the conventional cell, primitive cell, any cell. And so with AFLOW, you can calculate many different types of groups. You can determine the lattice point group. So this is the symmetry of the lattice points. So no atoms yet, just the lattice. If you were to take the reciprocal lattice, so this is the dual of the real space lattice, you can find this point group, and this is the Brillouin zone symmetry. We also calculate the factor group, as I mentioned, which is the unit cell symmetry. There's also the crystallographic point group. So that's when you consider the lattice and atom positions. And what is the point group? And the dual of this would be the irreducible Brillouin zone symmetry. We also calculate things like the Pearson symmetry group, which is another special group that's discussed in literature, the space group, and then the atom point group or the site point group, which is important for phonon calculations. And again, basically, this is the rotations about a particular atom. And all of these you can calculate with AFLOW-SYM. Another thing that I want to highlight that you can calculate, and all of these examples we'll be doing in some of the demonstrations in the next few minutes. But we can calculate what we refer to as the crystal spin symmetry. So for example, if we have a crystal structure, we can analyze the symmetry based on the lattice and atom positions, but we can also introduce the magnetic moment. So similar to what we were doing before we started the symmetry lecture, we were specifying the magnetic moment on each atom site. And this can have a consequence on what the symmetry is. So for example, if you put spin up on the corners and spin down on the center of the cell, so basically this is the exact example we did with BCC chromium. And if we were to use this information in our symmetry analysis, we would see that this is a degree of freedom that can break symmetry. And so we see that we get a lower space group. So we lost essentially this internal lattice translation. So it's P-centered instead of I-centered. And so this is an analysis you can do with AFLOW-SYM. You can specify the spin. And in general, we'll see this relationship that the crystal symmetry is a supergroup or subset of the crystal spin symmetry, because essentially spin is a degree of freedom that breaks symmetry. And we can do these with AFLOW-SYM. I wanted to highlight some of the representations of these different elements that you can get with AFLOW-SYM. So again, if you have a symmetry element, you can represent it mathematically in a couple different ways. So for translations, there's kind of one straightforward way. So this is just a 3x1 vector. So excellent question in the chat. So the question is the crystal spin symmetry the same as the magnetic space symmetry? And the answer is no. So in general, the magnetic space groups consider time reversal symmetry. And so, for example, if you were to consider the spin flip mechanism as time reversal symmetry, then basically you can get different symmetries. And so those would be the magnetic space groups. And I want to say that there's on the order of 1,000 different magnetic space group symmetry. And so in this case, the crystal spin symmetry is slightly different than the magnetic space group symmetry. Currently, we don't have this magnetic space group symmetry implemented in AFLOW. That's something that we've been kind of thinking about and working towards, but at the moment, we just consider this crystal spin symmetry. So, but yeah, that's a great question. And I think in the future, we're looking to incorporate the magnetic space groups. But yeah, great question. Okay, so so for the representations of the symmetry elements, so for translations, we typically represent them as a 3x1 vector. For these fixed point motions, so this would be rotations, inversions, and roto-inversions, we typically give them as 3x3 matrices. And then for fixed point free operations, so these would be the screws and the glides. Basically, it's a compound of the fixed point and the translations. And again, we can represent all of these in Cartesian basis set or a fractional basis set. But with these fixed point operations, there are many different ways that we can represent a subgroup of this, which are the pure rotations. And so if you're familiar with Lie groups or Lie algebra, these would be the SO3, this would be the SO3 Lie group. And so within this subset, you can represent the symmetry element in different forms. So the axis angle representation, the matrix generator, if you're familiar, this is the Lie algebra. Also quaternions, which are useful for graphics visualizations. So this is kind of a condensed representation. There's also the SU2 matrix, again, another form of Lie groups. And then also the SU2 Lie, corresponding Lie algebra. And so in AFLOW, you can get all of these representations when you calculate the symmetry elements. So again, depending on what application you may have for your research, AFLOW will give you all of these different representations so you can have these for your potential research applications. All right, so those are the explicit symmetry operations. There are also, I mentioned, the common symmetry descriptors that you may want to have at your fingertips. So for example, the space group number, the Hermann-Maguin international symbol for that space group, Schoenflies Hall symbol. And I want to mention that we're consistent with the international tables for crystallography. So this is kind of the de facto standard for crystallographic symmetry. So it has standard labels, standard settings, etc. Oh, so it looks like there's another question. What is the symmetry representation implemented in VASP? Excellent question. So the reason that we actually do this crystal spin symmetry is it's analogous to what is done in VASP. So again, if you introduce the magnetic moment for VASP, it'll also do its own point group symmetry analysis. And essentially it uses the spin as a degree of freedom that breaks symmetry. So essentially VASP does a crystal spin analysis, but just for the point group. So that's the symmetry representation that's done in VASP. Again, it's only the point group, not all of the other symmetry groups. And the other thing is that I want to mention is that, again, there's a slight difference between VASP and AFLOW because of the technical details that I mentioned. And a lot of times you may see that there's some tolerance problems that you may encounter in VASP because it doesn't have, for example, this tolerance threshold, adaptive scheme, etc. But yes, the symmetry representation implemented in VASP is, at least for the magnetic symmetry, it's analogous to the crystal spin symmetry. So hopefully that answers your question if it's related to this crystal spin symmetry. In general, VASP also does have a symmetry routine, again, but it only typically does the point group analysis, while AFLOW will do all of these other analyses. And again, we have noticed that there have been some tolerance issues within VASPs. So hence why we've been working on developing the AFLOW-SYM package. But yeah, great questions. Okay, so for the symmetry descriptions, I mentioned that we're consistent with this ITC. And so this gives the standard label, space group setting, and also what's known as the Wyckoff positions. So these are the site symmetries that are symmetrically equivalent within your crystal. And so if you're familiar with this resource, typically you would get information like the multiplicity. So this tells you the number of atoms that are a part of this symmetry operation. So the crystallographic orbit or constellation of points generated by the symmetry. It also has an arbitrary letter designation. So this A corresponding to this Wyckoff position, and then a representative coordinate. So typically it only gives one coordinate, and then you would need to basically expand out this coordinate to give the full constellation of points that are generated by this symmetry. And so again, this is something that AFLOW-SYM determines. It'll determine this Wyckoff position. And also with AFLOW, you can kind of convert back and forth between this representative position, which gives one position, and it can expand them out based on the symmetry to the 4 symmetrically equivalent positions. And we'll be seeing that today as well. So again, along with the ITC, there's also different setting choices. So for example, different origin choices or different lattices. And I'll show how you can control that with AFLOW-SYM. So for example, for rhombohedral systems, you can represent the crystal in a rhombohedral lattice. So that's indicated by this gray box here, or the hexagonal lattice, which is represented by one of these 3 lattices here, kind of on the outside. For monoclinic systems, you can have different unique axes. So basically, which axis is kind of perpendicular to this monoclinic plane. So you can specify that with AFLOW. And then also you can toggle between different origin choices for centrosymmetric space groups. So typically for these high symmetry systems, you can have different origin choices. So you can center on the inversion site or another high symmetry site. And again, you can toggle that with AFLOW. And again, we'll be seeing some demonstrations on this in the next few minutes. The other thing that you can calculate with AFLOW is the Pearson symbol. So for example, if you're familiar, this is an example Pearson symbol. And just for those who may not be familiar with what the Pearson symbol actually means, this first letter is the crystal system. And so for example, you can have a triclinic crystal system and basically these are the restrictions on the lattice parameters. You can have monoclinic, orthorhombic, tetragonal, hexagonal, or cubic. And so this lowercase letter corresponds to the crystal system. This second symbol, typically a capital letter, is the lattice centering. So basically it tells us for the conventional cell, what is the lattice centering? So if there's only one lattice point, then it's a primitive representation, or it has a P centering. In the conventional cell, if there's a lattice point on one of the sides, so it has 2 lattice points in the conventional cell, then it's C-centered. Face-centered, there's 4 lattice points in the conventional cell, and then body-centered and rhombohedral. And one thing that I just wanted to mention is that there is a relationship between the conventional cell and the primitive cell. So again, if you're familiar with some solid state theory or material science, when you're modeling these unit cells, there's kind of a ratio between the conventional and primitive cell. So it could be a 2-to-1 ratio, 4-to-1 ratio, and that's indicated by this lattice centering here. And then this last number, so is the number of atoms in the conventional cell. And so an easy way to think of this is you can just sum up the Wyckoff multiplicities, because the Wyckoff multiplicity tells you how many atoms, equivalent atoms, are in the conventional cell. So for example, for zinc blend, let's say you have zinc with this Wyckoff position and sulfur with this Wyckoff position. So you basically just add up the multiplicities, and there's 8 atoms in the conventional cell. So the Pearson symbol, actually for this zinc blende system, would be CF8. So maybe that was a review for some people, but I just wanted to highlight that. So one of the questions was, we can transform a conventional unit cell to the primitive one using AFLOW-SYM, and the answer is yes. And we'll be doing some exercises on that. So there's a subdirectory called conversions, and we can convert between the primitive cell, conventional cell, and also some other representations. So Niggli representation, Minkowski, if you're familiar. And so there are a lot of different ways you can transform your unit cell with AFLOW and AFLOW-SYM. So yeah, great question, and we'll see that probably in the next few minutes. All right, so, excuse me, I've highlighted some of the functionality that you can calculate with AFLOW-SYM. And the last two things that I wanted to mention before we get into the exercises are a lot of the functionality that I'm going to be discussing today is also online. And I'll try to show the counterparts to that. So the command line versus the AFLOW-Online functionality. And so you can calculate things like the space group Pearson symbol via this online interface, which I'll show. So that's at aflow.org/AFLOW-Online. And then the other thing that I want to mention is that towards the beginning of the lecture, I mentioned that AFLOW-SYM can work for all of the entries in the AFLOW database. And so we've used AFLOW-SYM to calculate the crystallographic symmetries of these systems. And we also have a JML interface, so you can visualize the structure. But since we know the symmetry, we can also visualize the transformations. So for example, if we were to go to a particular entry page, and I'll show this in a second in real time, but basically you can go to a symmetry tab and you can basically apply the corresponding rotations and see how the element or the atom positions map back onto the crystal. So actually, let's go ahead and do that. So let me go ahead and exit the presentation mode. There we go. All right, so if you'd like to follow along, I would encourage you to open a browser. And go to aflow.org. And so basically what we need to do is we need to find a particular entry in the database. So similar to what Professor Tower showed, we can go to the Mendelib search, and I'm going to look for sodium chloride. And I'm going to put two species, sodium and chlorine, and we're just going to search. We'll get a couple of results back, but really what I'm looking for is space group 225. And just in case I'm going too fast for people, I'm going to put the link in the chat. So this is the particular material that we're looking at. And so at the, so it looks like there's a question in the chat. Is there a function in AFLOW to symmetrize a structure with some tolerance if the structure is slightly disordered? So if you're wondering if by disordered, you mean that the atom positions are slightly from the ideal positions, yes, there is a function basically that you can use to essentially symmetrize. Essentially what you can do is, let's say you have your input geometry file, and I'll show an example of this, but the idea is that you take your geometry file, you can determine what the Wyckoff positions are, and then there's functionality in AFLOW to basically, given those Wyckoff positions, generate essentially the high symmetry, or basically the symmetry equivalent points. And so essentially that's symmetrizing it, because basically we kind of we've taken out that tolerance, so there might be a large tolerance value. And so basically you determine the symmetry, and then if you basically regenerate based on that symmetry, then it's almost like you have a symmetrized or an ideal representation of that system. So hopefully that's what you're referring to. Again, we'll see an example of this and I'll show it in the exercises. But yes, there is that functionality to do that. Excellent. Okay, great. Yeah, and I'll be sure to bring it up. So, but yeah, great question. Okay, so if we're on a particular entry page, we have the JML visualization at the top. And if you click on this symmetry tab, you can see all of these different symmetries. So basically there are 48 operations for this particular system. And you can rotate the cell. And what I want to do is I'm going to turn on the background supercell. So basically, so we can see how the atom positions transform. So I'm going to go ahead and scroll through this, and I'm going to find, let's say, a fourfold rotation. So you can highlight the axis of rotation. So that's indicated by this yellow axis here. And then you can apply it. And you can see how the atom, or essentially the atom set, rotates. And you'll notice it went outside the cell, but based on the background supercell, it mapped back onto the positions. And so if you were to apply this 4 times, as expected from a fourfold rotation, you're essentially back in the unit cell. And so that's the idea here. Another operation that I just wanted to show is a roto-inversion. So one of the reasons why I like the visualization is because it actually highlights that you might expect for a 3-fold roto-inversion that if you rotate it 3 times, you're back in the unit cell. But that actually isn't the case. For roto-inversions, especially for 3-fold roto-inversions, you have to rotate it or apply the transformation 6 times. So we rotate, then invert. So that's 1, rotate, invert, 2, rotate, invert, and you'll notice it's not back in the unit cell. And that's just the nature of roto-inversions. And we actually have to apply this 6 times. And that's consistent with the theory. If you remember from the slides that I showed, there were a constellation of 6 points for the 3-fold roto-inversion, not just 3. So again, the reason that I highlight this is that this can be used as a useful learning tool, and it can help to kind of clarify the different symmetry directions. So if you're having trouble visualizing, you can use this tool. Or for instance, if you're teaching a class on crystallography, this may be a useful tool to kind of show the different operations that you can have in a crystal. Okay, so are there any questions so far about up to this point about the symmetry visualization? Again, if there are, feel free to post in the chat. And then just the last thing that I wanted to mention before we get to the exercises is this example of, again, where symmetry can be important for calculating the properties of a material. And I mentioned this idea of phonons. So for modeling lattice vibrations in the crystal. And again, we'll see some of this modeling, I believe, the last day of the school. But basically, we can use symmetry to model these distortions. And again, we can reduce the cost of simulation by only distorting along symmetrically distinct directions. And then also we use symmetry to determine what the essentially the high symmetry K-paths would be for the phonon band structure. But also, since we're using these high symmetry distortions for the crystal, essentially we can reduce the number of distortions we need to model. And that's basically what's highlighted here. So there are a couple of different phonon packages in the community. And here, basically, we're showing the cost or the number of calculations versus the shell cutoff. And you can see that in general, that the AFLOW phonon package requires a fewer number of static calculations. So it's more computationally efficient. And part of the reason for that is because we're using symmetry very effectively to determine the unique distortions. And so we're able to reduce the cost of simulations, and there's a lot of techniques that we're using with symmetry and other techniques that are also being employed within the phonon package. And so we can actually see that with something like AFLOW-SYM and APL, you can model these with a reduced computational cost. So there's a question, is the visualization also implemented for spin symmetry systems? In general, we don't visualize the spin symmetry system, and that's because A lot of the systems that we calculate in AFLOW are either non-magnetic or ferromagnetic. So essentially, they would be, the spin systems would be the same as the crystallographic system. We don't really have in our database a lot of anti-ferromagnetic configurations, again, because there's a lot of degrees of freedom on whether or not we can have spin up, spin down, and generating those magnetic cells automatically is a challenge. And so we don't have a lot of those in our database, and so we don't visualize that at this time. I think if we were to add in more anti-ferromagnetic systems in the database, that's something that we would definitely, we have the functionality to do it. But at this time, we don't really distinguish. So a great question. Yep, no problem. Okay, so if there are any other questions about that lecture component, please feel free to let me know. Post in the chat. Otherwise, I'm going to go ahead and open the terminal, or so the virtual machine. And first thing that I'm going to do is I'm going to switch to the PDF version of the slides, so it's a little easier to see. So bear with me one moment. And let me close some of these tabs. Okay. All right, so hopefully everyone can see my screen okay. So essentially I'm going to have the presentation slides up that are kind of going to mirror the exercises, and then also we're going to have the terminal up. So let me go ahead and go down to the exercise part of the slides. And then we're actually going to start calculating these things. Okay, so again, please open a terminal, and then just so we're all on the same page, if you just type CD in the terminal and hit enter, it's going to take you to your home directory. And if you do ls, you can see what's in there. And I'm going to go into AFLOW exercises. If we hit enter, and we should see day 2 there. So everyone should see day 2 and have access to it. So please CD into day 2. And again, you'll see that the PDFs are here. But for now, we're going to go into A2, AFLOW Symmetry. And there are a couple of subdirectories for the exercises. And so the first one that we're going to go into, we're going to go in order, is space group. So one space group. If we do ls, you should see that we've got a couple of things here. We have a README, a geometry file, and also a Python script. So let's cat the README and see what we're going to be doing. Okay, so we have a particular crystal structure. We have the magnesium oxide rock salt structure given by this file. And we're going to determine the space group. So the number and the international symbol. We're going to calculate the Wyckoff positions. And then we're going to calculate all space group related data that AFLOW-SYM can give to us. And so there's essentially 3 command line option, or 3 commands that we can do. And again, these hints are essentially just the directions. So to calculate the space group, again, if you're familiar with the command line, you can either cat the geometry file into the command, or you can redirect it. So I may be switching back and forth, but just know that basically what we're doing is we're basically directing this geometry file to this command. So for example, we can do cat AFLOW --AFLOW s. Oh, sorry. I'm catting the postcard first. So cat MGO. And then you can do pipe. So basically, we're piping the output of that previous command to this other command. So AFLOW --AFLOW SG. So this is the space group command. And if we do this, you see that we get space group 225, as you would expect for rock salt. And then this is the international symbol. And again, on the left-hand side here, these are essentially for your own records. Again, when you're able to download the PDFs off the VM, you can refer back to this as a guide. All right, so that's the space group. If you want the Wyckoff positions, the easiest thing to do is hit the up arrow on the terminal to get to the previous command. And then just do AFLOW ---- Wyckoff. If you do this, then you get the space group number 225. This is the setting. So with respect to the international tables of crystallography, this is the first setting. Sometimes, as we'll see, there could be different settings. These are the ITC cell parameters. So again, these are the cell parameters for the conventional cell. So again, ABC and alpha, beta, gamma. So ABC are all the same as you would expect for a cubic type lattice. And then also they're all 90 degrees. Then we have the Wyckoff positions. So magnesium. Then we have the Wyckoff multiplicity, the letter, and then the site symmetry. And then this is the Wyckoff coordinate. So again, this is 0, 0, 0. And then this says that basically if you were to expand out this position based on the symmetry, then you would generate 4 symmetrically equivalent points. So those are the Wyckoff positions. And then if we hit up again, we can calculate, again, all of the space group related data by doing AFLOW ---- SG data. And so there's quite a bit of information here, but if you just scroll up, then we can see what we have here. So at the top, we have, again, the space group information, but we have all the different labels that you can have. So depending on if you have a preference to a particular designation or label, that's given here. We have again, the ITC information, so the setting and origin choice. Then we also have the general Wyckoff position. So basically for each space group, there's a generic Wyckoff position, typically given by XYZ coordinates. And so in this case, that's given here, again, in symbolic notation. And this is space group specific. If we scroll down, then again, we have the representative Wyckoff positions, similar to if you were to do the AFLOW ---- Wyckoff. And then at the bottom, basically, this is kind of that idealized or symmetrized version of the structure that was referred to in the chat. That was one of the questions. And so essentially, what you can do here is basically these positions were expanded out based on the symmetry into these, I guess, ideal positions. So how would you do this? Or I guess before I get into that, that's what you have with SG data. So, but if we wanted to, let's say, for instance, symmetrize, the other thing that you can do, which again, we'll see a little bit later, is you can do AFLOW ---- instead of Wyckoff, you can do Wycar. And this is slightly different than the Wyckoff positions. You'll notice that it kind of looks like the Wyckoff positions in the form of a geometry file. So essentially, we've created a postcard version of the Wyckoff positions, which we call a Wycar. And again, you can see it kind of as a lattice scaling, the lattice vectors, or sorry, the lattice parameters, and then you can see the Wyckoff positions. And if you were to hit the up arrow and redirect this to AFLOW, and if you do ---- VASP, this is basically telling AFLOW to convert that Wycar back into a postcard. And so this would be the answer to Zaid's question, that basically, can you symmetrize the structure if they're slightly distorted? And essentially, this is the procedure you would do. You would cat the postcard, determine the Wyckoff positions, and then feed it back into AFLOW to determine what the ideal or symmetrized version of the structure would be. Okay, so the next thing that I want to mention is, so these are all the command line variants, but we've also developed a Python module. So if you prefer Python and you have a Python workflow for your research, you can also use the AFLOW symmetry functionality via Python script. So if we were to go into the example Python script, so I'm going to use gedit, example.py. So you'll notice that I basically inserted a path to this Python module. So I'll show that towards the end, but basically we've developed a Python module that basically wraps around the AFLOW symmetry functionality. And as long as you have AFLOW installed on your machine, you can use this functionality. So I've put some comments here, but the idea here is basically we're gonna, if you're familiar with Python syntax, basically we're gonna open the geometry file, we're gonna instantiate the symmetry class and specify the path to the AFLOW binary. Again, you need to have AFLOW installed on your machine. And then basically you can run this AFLOW or this sim.get SG data. So again, it's similar to this SG data command, and it's going to calculate the space group data. And then we're just going to print out the output. And again, it's going to be in a Python dictionary. So you can basically, you'll have this key value pair. And so you can grab certain keywords, which correspond to particular descriptions or symmetry. Symmetry, it's things that were calculated, and you can print them out. So for example, we're going to print the space group number and the Wyckoff positions. And so we can just run this Python script, it's ready to go. So if we run Python example, basically it gave us a JSON back or a Python dictionary. And so basically as all of the SG data information that we saw before, but it's in this key value pair. And because it's in this representation, you can basically grab the space group number, so space group 225, and then also the Wyckoff positions, again, in this dictionary form. If you wanted to do this via the command line instead, so if you wanted to toggle between the human readable text or the JSON, you can easily do that. So if you go back to, let's say, the SG data command and do print equals JSON, for instance, and instead of getting that human readable text to the screen, you basically get this Python dictionary or JSON back. Or yeah, you get this JSON back. And so again, you can integrate this into your own workflow for maybe your research. So in the slides, I've basically kind of given, again, a guide to what the SG data output looks like, and that's given here. So are there any questions about how to calculate the space group, the Wyckoff positions, and how you can change some of these settings? Again, if there are, feel free to post in the chat. Okay, so if now we're going to go into the next demonstration directory. So if we go up one directory, we can go into SG settings, and we can cat the README. Okay, so I mentioned that in the international tables for crystallography, there are different representations or different settings that you can represent, for instance, your Wyckoff positions or the cell. And so again, I've reiterated that here on the slide. And basically you can toggle between the different settings with this -- settings flag. So again, setting 1 corresponds to what's listed here, and setting 2, basically they're all listed here depending on what the actual space group is. So again, in the README, I've also reiterated it here, but basically we're just going to play with this setting tag. So we can first go into the centrosymmetric system. So I've grabbed a centrosymmetric crystal structure, actually 2 of them. And what we're going to do is basically we're going to toggle between these settings. So first we're going to do this beta cristobalite postcard. We're going to cat it and do AFLOW -- SG data. Actually, let's go ahead and do the Wyckoff positions. It's a little bit easier to see on the screen. So we can do Wyckoff, and then setting equals 1. And so for a centrosymmetric space group, setting 1 is the origin is on the high symmetry site. So that's this site here, as you can see. So this bar 4, 3M. So the origin is here. But if we did setting 2, it actually does it on the inversion site instead. And now we can see that oxygen is on this site here. Or the origin is on this oxygen site here. So again, this can be useful if you wanted to represent things in a certain representation. And as always, if you were to use the ycar command, let's say, instead of ycof, then you're generating a ycar with this particular setting, and then you can regenerate the actual cell, and maybe if you wanted to model it in VASP, then now the positions have been expanded out in that representation. So that's for centrosymmetric. Okay, so it looks like there's a question in the chat. Missed this part of the setup. Piping the postcard to AFLOW with the AFLOW-SG tag returns an error. Error in X structure. So let me just go ahead and go back to that example just to make sure that we have the command correct. So essentially, you can either do, so cat MGO rock salt postcard. So just make sure first that you have this. And if you just do that, make sure that it's not empty or that you're able to do that. So if you just cat that postcard, you should see this. I guess hopefully you see that. If not, let me know. But then the idea here is that if you cat that postcard and then do the corresponding AFLOW command, you should get this. Are you still getting that error, or was the problem resolved? The other way that you can do it instead of piping is you can do AFLOW minus AFLOW-SG, and you can redirect the output this way, or make it an input. So hopefully that addressed your question. If you're still having a problem, please let us know. Otherwise, hopefully that clarifies your question. Okay. Yes, if anyone's having trouble or a similar problem, just please let us know. Excellent question. So are the current read the docs online somewhere for the Python? I don't believe. Sorry, I'm trying to think. I don't think we have them online anywhere. I believe we have them when you install AFLOW. We'll need to double check on that. Otherwise, for the Python READMEs, we can give you, we have a documentation on that, but I don't think that they're online anywhere that I recall. And we don't have a GitHub repo for AFLOW, so they're not on there. They should be available, I think, when you download the AFLOW source code, but if not, I believe we do have the READMEs for that, and we can send those out. Sometimes we just send them out during these AFLOW schools, and actually, it actually might be already given to you here. So if you go actually into the O2 AFLOW Symmetry subdirectory and you go into the Python module, I believe I included it there. So if you cat the README, okay, yes. So here's the README for the at least the AFLOW-SYM Python module. So yes, it's here. I don't believe they're online, but it is here. And again, we'll try to make these exercises and PDFs available to you after the school. But yeah, excellent. Okay, but yeah, great question. And then it looks like, okay, so it's resolved with the X structure error. It was just a 0. Okay, MG0, I see. Okay, not a problem. Okay, so if we go back to the SG settings, so I'll just highlight a couple of more so we can do the rhombohedral system. And again, you can do LS. We can see that we have a Caswell Silverite postcard, which I've already grabbed, and I know that it's rhombohedral. So we're going to do cat. Again, autocomplete is going to be useful here. And then AFLOW minus Wyckoff. Setting equals 1. And again, for rhombohedral space groups, setting 1 corresponds to a rhombohedral cell. So you'll notice that for a rhombohedral system, the A lattice ABC are all equal, and also alpha, beta, gamma are all equal, not 90, but all equal. And you'll notice the multiplicity of these Wyckoff positions is 1, 1, 2. So this is the rhombohedral setting. And then if you hit the up arrow, you can easily change to setting 2. And this is the hexagonal setting. So you'll notice the cell changed. It looks a lot larger. So you have A and B are equal. And then C is very large. So basically it's a really tall cell. And then you have 90, 90, 120. So that's consistent with a hexagonal cell. And you'll also notice that the multiplicities are tripled. And again, if you recall from the Pearson symbol, that's consistent with the lattice centering. So here, the ratio between the conventional and the primitive cell is 3. And so you can see that the Wyckoff multiplicity was tripled. And so you can see that this is a larger cell. And again, the reason why this is useful is because, again, if instead of Wyckoff, you did Ycar, you do setting equals 1, and then you pass it to AFLOW. Oh, sorry, AFLOW, and then do VASP. You've generated a postcard for a rhombohedral cell. And if you hit up and do setting 2 and use and pass it again to AFLOW, now you've generated a postcard for a hexagonal cell. So again, depending on your application, maybe you need to model the cell in a particular representation. And so this functionality can be useful for you. Or hopefully it's useful for you. And then the last example that I wanted to show was for monoclinic systems. Again, the procedure is the same, but I just wanted to highlight, again, if you were to cat this particular postcard, do Wyckoff, setting equals 1. So for a monoclinic system, the idea here is that if you do setting 1, you have unique axis B. So keep in mind that this 9.23 is the lattice parameter B, and that beta is not 90. If you were to change it to setting 2, you'll notice now 9.23, that's the unique axis, is now along the C direction, and now gamma is the one that's not 90. And so again, these are just different representations. Again, there may be a specific application where you want to model your cell in a particular representation, and that's how you can use these Wyckoff settings to kind of toggle between the different standard settings in the ITC. All right, any questions about the settings up to this point? If there are, feel free to post in the chat. Otherwise, I'll go into the extended crystallographic data. So this is basically where you can calculate. Oh. Okay, I wasn't sure if there was a question. So for this next exercise, so somebody has a question. Is it possible to reorient the vectors in the rhombohedral system? So that's a good question. Via the command line, I don't think that there are any specific options if you try to rotate it into a particular direction, at least via the command line. I know there's some internal functionality, but via the command line, I don't think you can specify maybe a particular direction that you want to orient them. So you may need to, okay. For example, 1, 1, 1 rhombohedral parallel to Z Cartesian. In general, that actually might be the default that we do. actually the default, I think, is the rhombohedral is parallel to the Z Cartesian. Essentially, what we show, sorry, let me scroll up. Essentially, it's this here, I believe, if that's what you're referring to. So essentially, the rhombohedral is essentially parallel to the Z Cartesian direction. So that is our default. It's oriented along that direction. At least I believe. But in general, yeah, via the command line, I don't think that we have some functionality that you can specify a particular direction. But great question. Okay, so for this next exercise, for the README, so we've calculated the space group. Now, if you want to calculate things like the Pearson symbol, the lattice type, so you can, again, as you might expect, to calculate the Pearson symbol, you do AFLOW Pearson, minus Pearson. So let's go ahead and cat this particular postcard, the web array. And then if we do AFLOW minus Pearson, you can get the Pearson symbol. So it's OI44. If you want the lattice type, you do lattice type. And this will essentially give you two things back. It'll be the lattice type, so ORCI, and then also the lattice variation. And so this becomes important for the band structure calculations. So essentially for the high symmetry K-paths, this would be the designation here. It happens to be the same for the system, but we'll see a little bit later on for the K-paths, these two strings could be different. There's also, if you wanted the Bravais lattice of the lattice, so if you were to ignore the atom positions, then what would the lattice type be? And in this case, it just happens to be the same thing based on a symmetry. And so if you wanted all of the possible crystallographic description data, which we call E-data, you can get it all in one go. So again, if you hit the up arrow and then do E-data, my terminal is running a little slow, but essentially you get a lot of information, and it's probably easier to see it in the PDF. So I'm going to show that here. But basically, it gives you a lot of the different common symmetry descriptions. So you get the real space lattice, the lattice parameters, the volume, the Bravais lattice of the crystal. So in this case, the example here was FCC. You get the point group of the crystal information. There's also a section for the SG data, so for the space group information. You'll also get the Bravais lattice of the lattice, so ignore the atom positions and what is the symmetry. You'll also get super lattice. So this is basically if we were to compare if we were to consider all of the atom positions of the same type in your crystal, so what we refer to as equally decorated, then what is the symmetry of that backbone structure essentially? And what is the symmetry of that? Then we have the reciprocal lattice information. So reciprocal space lattice itself, the parameters, and the lattice type and variation. And you'll notice that in reciprocal space, it's BCC, and in real space, it's FCC, as you would expect, based if you're familiar with the relationship between FCC and BCC in dual space. And then also you get different representations of the crystal. So the primitive representation or the conventional cell. So you get all of that with E-data. Okay, so there's a question. Is there an option for showing the structure type? NaCl, CSCl, ZN, S-type, etc. So actually that goes a little bit more into the prototype section and also the Extel Finder section. So there are options that you can actually compare a geometry file to a particular prototype. So these are what we would refer to as prototypes or structure types. So if you wanted to know whether or not your particular structure was a rock salt structure, for instance, that's not necessarily given by the symmetry explicitly, but we have extra functionality that says, okay, we know that this particular structure type is classified as rock salt, etc. So we'll actually see that a little bit in session 3, so later today, and also session 10 in Exfil Finder. And so that with the combination of these two modules, you'll be able to determine the structure type. But yeah, great question. And again, and they're all related to symmetry. So again, rock salt has a particular symmetry. So all of these modules essentially talk to each other because you need to know what the symmetry of your structure is to determine, this is rock salt. But yeah, great question. And we will be seeing that later on today and on Friday. Okay, so that's extended crystallographic data. Again, I just wanted to highlight that we do have a Python variant for this as well. And I'll at least open the Python script. But it's pretty similar to what I showed before. The only difference is instead of get SG data, we're doing get E data. And again, it's going to get all of the E data converted into a JSON. And then basically, again, you can use this key value pair functionality to grab certain values. So you get the Pearson symbol and you get the response. And let me just go ahead and close. And then if you wanted, close without saving. I didn't mean to modify. So we'll just do Python example. And again, you would get this analysis in a JSON as a JSON. And again, we queried certain things, Pearson symbol, Brillouin lattice, and you can see that here. Any questions about the extended crystallographic data? All right, so I think we'll do one more session or one more example, then I'll show the online functionality of what we've covered so far. And then we might take just a short break so people can get either, drink of water, more coffee. But we'll just do one more and then we'll take maybe a quick break and then we'll come back. But this next part, we're going to do conversions. So again, I think this was a question earlier. Can we kind of use AFLOW-SYM and the AFLOW software to convert between different representations? And the answer is yes. So there's kind of a couple of things you can do. You can convert between the representation of the geometry file itself and also the structure itself. So let's go ahead and cat the README. And here I've just listed kind of some different conversion techniques. We'll see a couple more a little bit later. But the idea here is that basically we can convert to what we refer to as an ABC car. So if we cat a particular postcard, we see what it looks like from the beginning. So this is what it looks like. And then if we were to pipe it to AFLOW minus ABC car, the only difference here is it's essentially, instead of this 3x3 matrix for the lattice vectors, we get the lattice parameters, which can sometimes be useful to see. Again, I already showed, but again, just to reiterate, you can do YCAR. So this is a YCOF representation of the postcard. It's pretty similar to the ABC car in the fact that it has the lattice parameters, but they're with respect to the conventional cell now. And you can see that we also have the space group and setting information, and then the YCOF positions, of course. And again, on the left here, this is just to reiterate what these mean. You can toggle between the primitive and conventional cell. So if we hit the up arrow, we can do AFLOW minus S prim, which stands for standard primitive. So again, what it's doing here is it's doing a symmetry analysis under the hood, and it's determining what the best primitive cell is based on the symmetry in the AFLOW convention. So again, when we do the band structure calculations, we represent the structure in a particular representation. And so that corresponds to the standard primitive representation. So it does a symmetry analysis. And then this is the convention that we have for the primitive cell. Again, the primitive cell is not necessarily unique. If you're familiar with, let's say, Ashcroft and Merman, I think they highlight this a great deal. that the primitive cell is not necessarily unique. You can have different representations of your lattice, but this is just one representation, and this is the AFLOW standard for FCC, for instance. If you just wanted a primitive representation, so not necessarily AFLOW standard primitive representation, you can just do AFLOW minus prim. And in this case, it does happen to be the same, but if you had a lower symmetry structure, you might observe different primitive lattices compared to the S prim. So you can convert to a primitive representation, or you can do standard conventional, so S-con. And again, you can see that this is the conventional representation of the MgO rock salt structure. And again, it's 4 times as large as the primitive cell, as you might expect. I think there were a few more. So I mentioned prim, S-con. You can also do Niggli and Minkowski. So again, Minkowski, I believe, is if you wanted to have the most orthogonal representation of your system, and Niggli is the shortest lattice vector representation. So in this case, again, this example may not be very interesting because rock salt is pretty symmetric, and so using Niggli versus Minkowski may not give you much of a difference. Looks to be the same here. Minkowski may just be rotated. Yeah, it looks like it's rotated. But in general, especially if you have lower symmetry structures, you can get a wide diversity of different conversions. But I at least wanted to tell you what the commands were. The other thing you can do is you can do supercells. And again, this is useful for modeling phonons in particular, but you can use, again, command line functionality. So you can do AFLOW minus supercell equals, and let's say you wanted a 3 by 3 by 3 supercell. And it's going to create basically a supercell based on those dimensions. And you can do 2 by 1 by 1, and basically any of these permutations, or any of these different supercell lattice expansions. So I think before we do maybe a quick break, I was just going to highlight the AFLOW-Online functionality corresponding to some of the things that I showed before. So if you go to aflow.org in your browser, and then if you go to AFLOW-Online here, then you can actually see some of the functionality that you can do online. So essentially, a lot of the symmetry functionality that I showed you can do online. And also for some of the other modules, again, we'll be referring back to AFLOW-Online, and you can do this essentially online. So I'll put this in the chat, AFLOW-Online. And so the idea here is you can upload a geometry file. We'll discuss a little bit later, but you can actually do any possible file format that AFLOW can understand. So AFLOW can understand PostCar, CIF, Quantum Espresso, ELK, FHI-AIMS, and then there might be 1 or 2 others, and I'll describe that again a little bit later today. But you can upload any one and AFLOW will auto-detect it. And so if you go to the symmetry section, then you can see some of the symmetry functionality that I've already described. So if you wanted to analyze the space group, so once you upload a structure, hit space group and hit submit, you can change the setting if you want. But otherwise, it'll give you the space group information. There's also the Wyckoff positions. Again, just analogous to what I showed via the command line, but online. So we have the Wyckoff positions, the Pearson symbol, the crystal point group. I'll show a little bit later the equivalent atoms. There's also the lattice type information. So this is kind of a subset of the eData command. So you can do real space, reciprocal space, or superlattice. So for example, you can get the superlattice information that's given here. And then if you wanted to convert between the different file formats, so if you do this, this is where basically this is the comprehensive list of what AFLOW can understand. So ABC car I showed, There's also ABINIT, FHI Ames, SIF, ELK, Quantum Espresso, VASP 4 or 5, and the YCAR. And so you can easily convert. Let's say you wanted the SIF. Then you get the SIF version of this geometry file. I'll show in the next slides, but you can also, after the break, you can also change the symmetry tolerance. That's here. And then also the output type. So right now we've been doing plain text, but again, there's the opportunity for the JSON. So for example, if you wanted the Wyckoff positions in a JSON format, you have that here. So again, we're going to go back to the terminal. And now we're going to continue with the exercises, and we're going to go into subdirectory 5. So we have a couple more examples that we're going to show, and then there's going to be some exercises where we'll go into breakout rooms and we'll kind of test some of the things that we've been discussing on our own, and then I'll show you the solutions at the end. But okay, so if we go into symmetry ops, and we can cat the README to see what we'll be doing in this exercise. So this is where we're actually going to calculate the explicit symmetry operations. So like I mentioned before, these would be the rotations, roto-inversions, glide planes, screw axes in the different, and arranged in the different type of point groups or factor groups. So for example, I mentioned that there's many different types of groups that you can calculate with AFLOW. And again, they're listed here. And basically all of these analyses are going to be saved to a file of this type. So it's going to be aflow.p group xtol, a group, s group, etc. So basically this is kind of the mapping between what the analysis is and where it's written. Again, you can kind of toggle between the different printing options. You can do a human readable text or a JSON if you'd like to manipulate it later in your own workflow. And so to do this analysis, essentially all you have to do is, again, like the usual procedure, you cat the geometry file. In this case, it's magnesium oxide rock salt in a conventional representation. And then we do AFLOW -- AFLOW-SYM. So essentially this is the namesake command. And it actually prints quite a bit to screen. And if you remember from the lock file that I showed in the first part, when we were doing the AFLOW-IN, and actually if we were to run the AFLOW-IN, this is basically what would be generated. And this is part of the symmetry analysis. So actually what I'm going to do is I'm going to redirect this to sim.log so we can actually open it and kind of read it a little more clearly. But if we do gedit sim log, we can basically see what's being output to the screen. So basically, it's basically logger information. So basically it tells you what the starting symmetry tolerance is in angstroms. Then it's telling you what analysis it's doing. So it's doing the point group analysis. It's telling you a shorthand version of what symmetry elements were found. And then if we were to continue to scroll down, basically then the reciprocal lattice point group, so K lattice. Then after that, the F group, which is the unit cell symmetry, or the symmetry elements confined to the unit cell. So that includes rotations, followed by translations, if there are any. So if we scroll down, so there's a lot of information. I won't go through all of it, but basically it's telling you what the analysis was performed and a summary of the different operations. And then at the end, it tells you which atoms were symmetrically equivalent. So this is analogous to the Wyckoff positions, but essentially it's the equivalent atoms in your unit cell. So it's slightly different than the Wyckoff positions. All right, so if you were to do ls, you would also notice that there are some files that were written. So basically the files that I mentioned before, aflow dot and whatever the group analysis that was performed. So if we were to open one of these, again, I'm going to unzip it first. So let's just do xz minus d, and let's go ahead and open the aflow.p group. So first we're going to unzip it, and then gedit aflow.p group .out. And if we were to look at this, basically we see that we have all of the point group operations for this analysis. So there are 48 point group operations, and then they're listed here. And you'll notice that there's quite a few different representations that are shown, and that corresponds to basically one of the slides that I showed before of the different representations for each element. So for example, for symmetry operation number 2, the second one that was found, it's a roto inversion or mirror plane. It has the Schoenflies designation. It has the 3x3 matrix in Cartesian and fractional coordinates. There's this matrix generator here, and basically some Lie algebra, so the coefficients SU2. We have the axis angle here, the quaternion vector, so that 4x1 vector, and then the quaternion matrix, which is a 4x4 matrix. And then there's a Boolean that says whether or not it's an inversion. So that's actually summarized here in the slide. So again, if you kind of need to refer back at a later date, I've basically shown what's calculated here. So that anything that's related to a point group operation, so just rotational and inversion and roto inversion symmetries. But if you include translational invariance, then you would get the factor group. So we're not going to open the file, but essentially it would look exactly the same as the point group. Granted, the operations might be different, but we also include the internal translations here. So let me actually zoom in a bit. So for factor group, you'd have the same information plus the internal translations in Cartesian and fractional coordinates, and then the mapping info. So basically this tells you the mapping indices, how the atom indices match between the original atom set and the transformed atom set. So there's this mapping information here. And then for the space group, so aflow.s group, again, you have the same information, but now you also have the lattice translations, again, in Cartesian and fractional coordinates. And so that's the space group. Excellent. And so it looks like the files online are available for download now. So thanks for looking into that, Dr. Esters and Dr. Osis. Okay, so I'm going to close this file. And so again, there's the different analyses that are performed here. And if you wanted to just do one instead of maybe all of them, so basically AFLOW-SYM, if you do the AFLOW -- AFLOW-SYM command, it'll do all of these in one go. And this is useful because, as I mentioned, there are consistency checks with AFLOW. So if you remember that tolerance number line, basically AFLOW is performing internal symmetry checks. So it's making sure that the factor group is consistent with the point group, because there are some conventions that need to be followed. And so if you do this all in one go with the AFLOW-SYM command, you have that advantage of having everything being consistent. But if you just wanted maybe a subset, maybe you just wanted the factor group instead, and you didn't want to calculate all of these things, there are some separate commands, which I highlighted some in the slides here. But basically, if you were to run some of these commands separately, then you would have, you can do that analysis. So for example, if you just wanted to do cat MGO rock salt postcard, AFLOW -- F group for factor group, then it's just going to do those two. So it has to do the point group and then it does the factor group. So basically it's only going to do up to what you requested. So it looks like, okay, so it looks like there's still some issues with the files. We can continue to work on that and we'll let you know. If you're still having issues, we can work on that. But okay, so you can perform essentially any of these subset analyses if you just do AFLOW minus minus, for example, P group XL, etc. And again, just one thing that I forgot to mention that I wanted to is let's go ahead and look at the factor group. So we'll unzip it. And then actually let's use gedit. One thing I want to mention is, again, this idea of the factor group being the unit cell symmetry. If you recall, we are working on the conventional representation of the rock salt structure. And so in general, if you're familiar with the symmetry of rock salt structure, you might expect 48 symmetry operations, but the unit cell is 4 times as large. And since the factor group is the symmetry of the unit cell, the factor group operations are also 4 times as large. So 48 times 192, as you would expect, or sorry, 48 times 4 is 192. And so that's how many factor group operations. So again, it's highlighting that the symmetry operations are with respect to a particular unit cell, in this case, the conventional cell. All right, so are there any questions about the symmetry operations? Again, as always, there is a Python version as well. And again, just like the get SG data or get E data, you would do get symmetry. This is going to calculate all of those different point groups that I mentioned. It's going to be saved to a JSON. And then basically here, you could print out all of the factor or all of the operations, but here I've just printed the cardinality or the lengths. And so if you were to run this, basically it's doing the same analysis. Python example. And so here, just what I printed was the cardinality of each group or the order of each group. And then I printed an example factor group operation. So again, it's the different representations of this symmetry element, but in a JSON form, so you can easily manipulate it or integrate it into your workflow. All right, so any questions about the symmetry operations or how we calculated that? If there are, feel free to post in the chat. Otherwise, there's a couple more demonstrations that I'll do, and then we'll get into the exercises. So next, we're going to be going into the crystal spin subdirectory. So this is 6 crystal spin. So this is if you wanted to do that, if you wanted to incorporate the magnetic moment into the symmetry analysis, like we mentioned before. This information isn't explicitly given in the postcar. Typically for VASP, it's given in the in-car, for instance, or maybe it's calculated after the fact in the out-car. So if you wanted to do this via the command line, the way that you would do this is, again, you need to have a particular geometry file, and it needs to be large enough or be able to encapsulate the magnetic ordering. So again, we're just using this chromium BCC example that I mentioned before. It's in the conventional form because it needs to be large enough to capture this antiferromagnetic ordering that we're going to be doing. And so what we're going to do is we're basically going to put spin up on one site and spin down on the other site via this magmom option. Again, very similar to the magmom tag in VASP, it's just via the command line. So we're going to cat the postcar. Then we do AFLOW minus minus. We can do this for the space group, for instance. And if we just run it as is without magnetic moment, we get space group 229. But if we hit the up arrow and then add magmom equals 1, -1, for instance, you'll see now we get space group 221, and that's the exact example that I showed in the slides. So that's collinear magnetism. You could also do non-collinear. And again, you just need to make sure that you specify the correct number of basically magnetic moment components. So it needs to be modulus 3. And so again, you can see that we've done this. If you had an error or a typo, you'll get an error saying that we couldn't detect between collinear and non-collinear spin. So AFLOW will auto detect which one you do. And then basically, since the number of inputs was wrong, you'll get an error. So you may just need to check that you did that correctly. So you can do this for the space group. Basically, anything that considers the atom positions, you can also do the magnetic moment analysis. So for the Wyckoff positions, you can do the same thing. The E data or the symmetry operations themselves, if you add this magnetic moment flag, you can do that. The other thing that I want to mention is that since we're working with VASP so closely, we can also pass in the path to the in car, the out car. So if you didn't want to specify it explicitly via the command line, the actual magnetic moments, you could also do the path to the in car. And this will read that magmom tag in the in car and pass it to the analysis. Same for the out car. In the out car, it has the magnetic moment information. So you could do path to the out car file, whatever that path is, and it will integrate it into the analysis. And as always, there's the Python version. And basically, the only difference here is you're adding an option to the analysis. So magmoms equals 1 and -1. And so with that, if you were to run this Python script, we calculated the space group with and without spin. Any questions about the crystal spin analysis or how you can do that? All right, so we've got, I think, maybe 1 or 2 more exercises or demonstrations, and then we'll go into the exercises. So next is this idea of the symmetry tolerance. So I mentioned that the symmetry tolerance can be important because we can essentially get that tolerance number line. So we can get a tighter or looser tolerance, or using a tighter or looser tolerance value, we can observe higher and lower symmetry. And the reason why it's useful to be able to control this option is maybe an experiment, maybe you had a high resolution experiment and you're able to identify the atom positions kind of to a high degree, or maybe you have lower resolution. And so you can kind of use the tolerance kind of to toggle between different space groups. So for example, sometimes in experiments, they may say it could be, space group X or space group Y, but it's difficult to determine based on, maybe the resolution of the experiment. And so actually with this tuning of the tolerance, sometimes you can actually capture that phenomena. And again, I think it's related to a question that we had before of basically kind of using the tolerance threshold to see whether or not we're going to break symmetry or not, for example. So that's where this tolerance value can come into play. So how do we actually calculate this or use this option? So again, I mentioned that there are essentially, there's 2 default tolerances. There's the tight and the loose, which are based on the minimum interatomic distance, or you can specify a number yourself. So what we're going to do in this exercise is we're going to take this particular postcard and we're going to basically change the tolerance value and see if the space group changes. So again, here's some hints on how to do it. So again, if you download the exercises later, this README will kind of serve as a guide for you. So if we do cat postcard, we do AFLOW minus AFLOW-SG, and then to specify the tolerance for the particular symmetry command, you add an equal sign to the command, and then you say what the tolerance value will be. So if we have some string aliases. So if you put tight, that's the default tight value. So minimum distance divided by 100, or loose, which is minimum distance divided by 10. So if we do this, we get space group 204. But then in the exercise, I said, let's go ahead and now change it to 0.005 angstroms and 0.001 angstroms. So if we hit the up arrow and do 0.001, 195, and I did it out of order, but 0.005, you get space group 200. So these are different classifications of this structure. And so again, this might actually be mirrored in an experiment. And actually, this is indeed what we see. So for example, I'm going to, we're going to see this in the next section, but I'm going to go to the AFLOW prototype encyclopedia, which is where we list some common crystallographic structures that you can generate with AFLOW. Again, I'm kind of giving a preview into the next session. And basically, I'm going to find that might have been too loose of a search. Let me go ahead and get, so it's space group 204. Sorry, bear with me. I should have looked this up beforehand. So I'm just trying to find this guy, 204 and CI34. Okay, must be this guy. Perhaps not. I'll find it probably in the break. I should have given the URL. I thought I did. But essentially, what I wanted to show is that actually in literature, we found that this particular geometry file has been classified as either space group 204, 201, or 200, whichever the, yeah, so 204, 195, and 200. And you'll also, if you're familiar with symmetry subgroups relationships, that actually space group 200, one of its subgroups is 195, and one of its supergroups is 204. And so you can see that basically with this tolerance tuning, we can observe kind of the subgroup supergroup relationship. And so one other thing that I want to mention is maybe you wanted to do a scan of the tolerance. So basically, maybe you don't know exactly what tolerance you want to use, and you kind of want to see how stable the space group is with respect to a tolerance value. And so you can automatically do this tolerance spectrum scan. So again, you can do cat and AFLOW minus AFLOW SG, and then tolerance spectrum. And you can do the starting tolerance. So we're going to do 0.001 and then colon. And then we're going to go up to 0.1. And then we're going to do 25 steps. So AFLOW will automatically determine what the step size should be. And then basically you can kind of see what the space groups are at different tolerance values. So one thing I want to mention is that at each value, AFLOW might do this tolerance scan for each one, because again, it's going to try and find consistent symmetry. So if you wanted to find where those void regions are that I mentioned, so possible confusion regions, you can add no scan. And basically this will prevent it from doing that adaptive tolerance at each value. In this case, I don't think it makes a difference. I think we find consistent symmetry at all the tolerance values. But if you were trying to reproduce this tolerance number line that I showed a little bit earlier, if you wanted to recapture this, you would need that no scan option. And again, of course, there's the Python example. In the interest of time, I'm not going to show it. But if you run it, you can do the same analysis by basically adding in the tolerance as an input. And you can see you can get, based on the different tolerance inputs, you get the different space group results. Any questions about the tolerance or how you can modify the tolerance with AFLOW-SYM. Again, I only showed AFLOW-SG, but you can also do it for other commands, the Pearson symbol, Wyckoff, positions, etc. Essentially all of the different symmetry commands. All right, so the last demonstration before we go into breakout rooms is we are going to go to the K-paths. So we kind of saw a little bit of this when we were doing the band structure calculation yesterday. Excuse me. But I just wanted to show you how you could do this via the command line. So if you just have a geometry file, you can basically determine what the high symmetry K-path would be in the AFLOW standard based on the articles that Dr. Osis sent in the chat yesterday. But we can do cat MGO and then AFLOW -- K-path or BZ directions for Brillouin zone directions. And this will give you essentially that K points, kind of looks like that K points file. So the line mode, so basically the FCC, and basically it gives you the high symmetry K points. And if you were to feed this into VASP as the K points file, then it would do this line mode and you get those high symmetry K paths. And above this is essentially the structure consistent with this orientation of the K points. And so this is defined essentially on the left-hand side here. So this is the AFLOW standard for determining the Brillouin zones. So essentially you take the original lattice, take the dual of it. So basically convert it into reciprocal space, do a Minkowski transformation on the lattice. So basically that makes it the most orthogonal lattice in K space. And then you perform the dual back in real space, and that gives you essentially the S-prim representation of that structure. And so there are 25 of the Bravais lattice definitions, or 25 Brillouin zones that have been defined by actually Professor Curtarolo and one of the postdocs that we had in the group at the time. And actually, if you go on to Wikipedia and look at Brillouin zones, these pictures may look familiar, and these are actually the Brillouin zones that were defined by our group and Professor Curtarolo. And so basically I showed the command already on how to generate this. And so you can basically use this for determining the high symmetry K-paths for your simulation. All right, so before we get into the exercises, I just wanted to briefly show the Python module. I showed it a little bit before, but basically go into this directory, as was mentioned in the chat. The README for the actual Python module is located here. There's some example scripts, and then actually in this Python file is the actual module itself. So that's given here. And so basically we've kind of predefined these functions. So basically this get symmetry method, get e data, all of this is here. And if you'd like, we've kind of only given you the three, but now that you know kind of the syntax for the command line, you could easily add more functions. And a lot of these things are JSON friendly or Python dictionary friendly. And so you could add some more functions if you'd like. All right. And so with that, I think we'll go ahead and we can do the exercise. It looks like we've got about 30 minutes, so we should be good on time. So again, here's some information about the Python module. I guess before we do the exercises, again, I'll highlight, I've shown that some of these functions are available online. Again, the ones that we covered after the break, if you wanted the symmetry group information, that's listed here. So you can calculate that online. And then I think, we also covered crystallographic data. So again, a lot of these you can do online. Okay, so with that, we have some exercises. So if you go into CD exercises, we have essentially 4 different exercises that we'd like you to do. So in each of these subdirectories, there should be readmes, I believe, on what to do. But they're also listed here in the PDF. So I'll briefly go through it and then we'll go into the breakout rooms. So, but the idea here is in this first example, we're going to determine the space group and Wyckoff positions for these 2 structures. Do the space group settings change the results? So using that setting flag, and does the tolerance change the space group? Next is to calculate the Bravais lattice of the crystal Pearson symbol for this particular structure. And what is the ratio between the conventional and primitive cell? So I tried to highlight that idea a little bit, so hopefully that makes sense. And is the Pearson symbol consistent with that? Next is a K-path example. So just determine the high symmetry K-path for this structure. And then the last one is to analyze the space group operations for the zinc blende structure in the conventional cell, and to comment or to calculate and then comment on the cardinality or the order of these point group operations. And do they make sense based on the ratio between the primitive and conventional cell? So let me go ahead and share my screen. And so there are a couple things that I wanted to mention. So first was I was trying to find that particular prototype that basically has a different symmetry classification. So this was the structure that basically when we were comparing the, sorry, let me move the Zoom stuff. There we go. Basically, this was the system that when we changed the tolerance value, we got a different space group. And what I wanted to show is actually, so this is a particular prototype structure that we're familiar with. And we actually see that actually in this experimental reference, it was originally reported as space group 195, which is what we've classified it as, but some of the references say that also space group 200 is also a possible space group. So again, there's kind of some ambiguity in what the experimentalists determined as the space group. And so by playing with this tolerance values, we can kind of see that as well, that basically depending on the resolution or the tolerance, you can get different symmetry classifications. So that's kind of what I wanted to highlight in that example. So, and it just took me a second to find this particular page. Okay, so with that, before we get to the exercises, I guess in Dr. Esther's group, there was a really good question about what the difference between the Lau class and the crystal class. So actually in the example that I showed, they're actually the same, but the difference is the crystal class corresponds to basically the point group. So essentially kind of this point group operation here, that's the point group designation, basically similar to this, but the Lau class includes additional inversion symmetry. So I didn't really get to talk about the details of the different symmetries, but one of the symmetries that you can calculate is the Patterson symmetry. So there's this P group Patterson, and essentially this is the symmetry in reciprocal space. And here's a great graphic that is really useful, I think. But essentially, let's say you have a crystal, and then you basically have these vectors between the crystals. So basically these distances or vectors connecting the different atoms in the crystal. And basically, it's in reciprocal space, it's basically the symmetry of these vectors. So basically you can define a vector going in the positive direction, we'll say, or the negative direction. And inherently that adds inversion symmetry. And so basically the relationship between the crystal class and in the Lau class is the Lau class adds that additional inversion symmetry if it doesn't already have it. In this case, it already has kind of this inversion symmetry, but if it didn't, then that's where you would see the difference. So the Lau class is very closely related to the Patterson symmetry, where essentially it's the symmetry of this vector set. And again, because you can have positive and negative vectors, you have that inversion symmetry. So hopefully that answers that question. And again, I think the example that I chose, there wasn't really, there wasn't a distinction there, but that's a great question. Okay, so it looks like we've got maybe a couple more minutes, so I'll briefly go through the exercises. If anybody had a specific question, I'd be happy to take it. But if not, I'll briefly go through what you would have done for these exercises. Let me just arrange my screen a little bit. There we go. Okay. So if you're at the terminal, the first one was hopefully somewhat straightforward. Basically, I gave you all the commands that you needed, but basically the idea here is that I wanted you to calculate the space group and Wyckoff positions for these two structures and play with some of the settings. So I'm going to do the beta cristobalite just as an example. The procedure is the same for an argite, but you can do AFLOW minus AFLOW-SG to get the space group, or in one go, you can do AFLOW minus Wyckoff. And in this, you'll get the space group at the top and then also the Wyckoff positions. So this is what you'll see. And then to see if the setting does anything, you can just add minus setting equals 1 or 2. We already did 1 by default. So if we do 2, you do see that actually you get a change. You'll notice if you did an argite, you would not see a change. And that's because that particular orthorhombic system only has one standard setting. And so it's not going to give you a second setting because there isn't one that exists in the ITC for that. And you'll see that this is a centrosymmetric space group. So basically the origin changed Wyckoff positions. And again, you could play with the tolerances by basically, let me go ahead. And you can use the AFLOW-SG, and then I showed you that tolerance spectrum command. So this is a nice way to easily scan to see if the space groups are going to change. So you can put the lower bound, colon, upper bound, colon, and then the number of steps. And you can see that it's pretty stable across a wide range of different tolerance values. So that was the first one. And the next one was basically to kind of get the difference or calculate the bravuritis of the crystal, the Lau class, which I mentioned, kind of the distinction there, and then the Pearson symbol. And the easiest way to do that, you could have used some separate commands, but I recommended using edata. And you could easily find that information. And then the question was, what's the ratio between the conventional and primitive cell? So at the end here, you get the conventional cell, so 8 atoms versus the primitive, which has 2 atoms. And if you looked at the Pearson symbol, it was OF8. And so is this consistent? Basically, I wanted you to kind of remember back that a face-centered cubic lattice in the conventional cell is 4 times as large as the primitive. And so basically, it was basically 4 or 8 atoms versus 2 atoms, so a factor of 4. And then also the Pearson symbol has an 8 here, which says that there's 8 atoms in the conventional cell, which is what we saw. So again, there's kind of these consistencies, and again, that's something similar to one of the consistency checks that AFLOW does. I'll kind of skip this next one, the K-path. Basically, all you had to do was cat the postcard and then run AFLOW minus K-path to just kind of see. So we'll skip that one. I think that one was straightforward, but I'll happily take any questions during the break if anybody had a question about that. But this last one was basically to do the minus AFLOW-SYM. So calculate the symmetry operations for this zinc blend in the conventional cell. So per the README, I think I gave you a suggestion. Run the AFLOW-SYM command. So we cat the postcard, then AFLOW minus AFLOW-SYM. Basically, we have all that information there, and basically count the number of lattice point groups, the crystallographic point group and the factor group. And so you could easily just open one of these files And then at the very top of each file, let me just go ahead and unzip all of these guys. And if you looked at the AFLOW P group.out, there's 48 lattice point group operations given at the top. Then the crystallographic point group. So that's essentially the same, but we have P group underscore extol.out. This one has 24. So in this case, we see that by introducing the atoms into the lattice, or essentially introducing a basis, we see that we've broken some of the symmetry with respect to the lattice. So we have a fewer number of point group operations. And then if we look at the F group, we see we have 96 factor group operations. And the question was, what is the ratio between the factor group and crystal point group? So the ratio is 96 to 24. So that's a factor of 4. And kind of, does this make sense? And again, this is a zinc blende structure, which is FCC. And again, relating back to example 2, the ratio between the primitive and conventional cell is 4. So 24 times 4 is 96. And again, that's because the factor group gives you the symmetry operations with respect to the conventional cell, since that's what was fed in. So other than that, I believe those were all the exercises. If there's any questions, feel free to let me know. Otherwise, the last thing that I wanted to mention was I got a question in my group about, what if you forget about these symmetry commands? You can run aflow -- readme equals symmetry. I'm going to pipe it to a file or pass it to a file. And just to kind of show you what's in there. Oh, wrong readme. So essentially, we've got some information, a general overview, basically a quick list of a lot of the relevant commands. Again, we didn't get a chance to cover a lot of these. A lot of them are kind of specific analyses, but they're all here. And then basically a comment on the self-consistent symmetry, tolerance, the tolerance spectrum, that's relatively new functionality, the crystal spin or magnetic analysis, cell choices, output formats. So again, JSON versus text, and then basically a comprehensive list of all the options. So I only presented some of the common options, but there's a lot of different options you can play with or add to the command to hopefully kind of cater to different scenarios. And so that's all listed here. And then if you're interested in kind of the theory or the information about the algorithms, there's the article here, the AFLOW-SYM article, which I've given you the DOI for.